let's talk about the humble transformer. It's this silent, hard-working device that's pretty much the backbone of our entire electrical world. But behind its amazing utility, there's a hidden story. One about wasted energy and also a pretty brilliant built-in safety feature. So yeah, let's unpack all that.
First things first, transformers are absolute engineering marvels. I mean, with zero moving parts, they can hit efficiencies as high as 99%. Just think about that for a second. That's an incredible number for any kind of machine.
So that kind of begs the question, right? If they're 99% efficient, what's the big deal? What could possibly be the problem here? Well, it turns out it's all about what happens with that last 1%, especially when you consider the massive scale we're talking about. And here it is, that tiny little percentage of loss. When you add it up across the millions and millions of transformers on the grid, well, it can account for more than 3% of all the electrical power generated on the entire planet. That is a colossal amount of energy just poof, wasted as heat. A picture like this really drives home the scale of what we're dealing with. Every single transformer in this huge, sprawling grid contributes its own tiny little fraction of a loss. But when you multiply that across a global network, that tiny fraction suddenly becomes a really significant global energy challenge. So, to understand how we can fight this energy loss, we first have to meet the two main culprits. You can think of them as the two energy thieves that are hiding inside every single transformer.
Okay, what's really interesting here is how the problem gets split in two. On one side, you've got core loss. The easiest way to think about this is like a car that's idling. It's a constant drain happening 24/7, just as long as the transformer is energized. Then, on the other side, you've got copper loss. This one's all about performance. It only really shows up when you're actually using the power, and it gets way worse the harder that transformer has to work. So let's tackle that first problem, that constant nagging core loss. It turns out, engineers have come up with some incredibly clever ways to tame the magnetic field that's causing it. Core loss itself actually breaks down into two little parts. Hysteresis is basically the energy that gets burned just by flipping the magnetic poles back and forth, 50 or 60 times every single second. But the really fascinating one is the eddy current loss. Think of these as tiny, wasteful whirlpools of electricity spinning around inside.
Right, so think of eddy currents just like eddies in a river. They don't actually help the water flow downstream, do they? Nope, they just swirl around in circles, creating drag and wasting energy. Well, in a transformer's core, these electrical eddies are doing the exact same thing, just generating useless heat and wasting power.
Now, the solution to this is a fantastic two-step engineering fix. First, you use a special kind of silicon steel that magnetizes really, really easily, which helps take care of that hysteresis loss. But the real genius move here is the laminated construction, which is designed for one specific purpose: to fight those pesky eddy currents. And this just shows you exactly why it works so well. Instead of having one big solid block where these huge energy-wasting eddies can form, you have hundreds of super thin sheets, and each one is insulated from the next. The eddy currents can't cross those insulated gaps, so they get trapped in these tiny, weak little swirls. It's such a simple, elegant, and incredibly effective solution. Technology never stands still. The next frontier in this fight is something called amorphous metal cores. Now, these are definitely more high-tech and more expensive, but they can cut core losses by another 60 to 70%. They really are a major leap forward in pure efficiency. All right, so we've dealt with that constant core loss. Now, let's move on to the other thief in the system, copper loss. This one is all about the price you pay for the power you actually decide to use. So this relationship right here, I squared R, this is the crucial thing to understand. The loss comes from simple electrical resistance in the copper windings. But because it varies with the square of the current, the penalty for working harder gets severe, and it gets severe fast. What that means is, if you double the load on a transformer, you don't just double these losses, you actually quadruple them. So fixing this one isn't so much about clever physics like with the laminations, it's more of an economic and a design choice. You can use better materials or improve the whole system, but really the biggest factor is just choosing to invest in a more efficient transformer right from the very start. And this table just tells the whole story, doesn't it? Look at the purchase price. Sure, the high-efficiency model costs more upfront, but then look at the losses, both the no-load and the load losses. They're way lower. And when you calculate the cost of all that wasted energy over the transformer's lifetime, the total owning cost is dramatically less for the more efficient model. It's not even close.
This quote really just hits the nail on the head. The initial sticker price isn't the real cost. The real cost is that price tag plus the cost of all the energy it's going to waste over the next 20 or 30 years of its life.
Okay, we've talked a whole lot about efficiency and loss, but a transformer does another job that's absolutely critical. And this one isn't about saving energy, it's about saving lives. It's all about something called isolation. Just take a look at this basic design. You see the power comes in on one coil, it creates a magnetic field, and then that field induces a current in the second coil. Now, what's the most important part of this entire picture? It's the gap. It's the fact that the two coils never, ever actually touch. This very simple principle is called electrical isolation. It means there is no direct wire connecting this super high voltage power grid to the circuits inside your home. The power literally has to jump across that gap using nothing but magnetism. And that magnetic link is the whole key to safety. It creates a physical barrier, literally an air gap, that separates the dangerously high voltages of the transmission network from the much, much safer voltage that comes out of your wall socket. It's a really profound and elegant safety feature that's just built right into the physics of how the device works. So let's just sum it all up. Transformers are hyper-efficient, but we've seen how their sheer numbers make those tiny losses a huge global problem. We now know we can fight those losses with smart materials and clever construction. We've also learned that investing a bit more upfront in efficiency almost always pays for itself in the long run. And finally, and maybe most importantly, their very design gives us a fundamental safety barrier that protects all of us every day. You know, it really makes you think. This is a technology that's over a century old, and yet it is still the absolute backbone of our modern world. So as our demand for energy just continues to soar, you have to wonder, how much more energy could we save by rethinking the design of this essential device? What other innovations are still out there waiting to be discovered?
Thanks for watching, and please like, share and subscribe for such more content and appreciation. Make sure to comment your questions and